no chat, tá, pessoal? E aí a gente vai lendo no final. O professor Alcemir vai tomar conta aqui da palestra. Depois eu vou ter que dar uma saidinha para apresentar um paper no SB Cards, mas eu volto assim que eu terminar lá. Aí o Alcemir vai controlando a palestra, tá, Alcemir? E vendo aí, né, as questões, as perguntas e tudo mais, e interagindo com o David. Tá bom? Okay, so let's switch to English now. First of all, thank you, David, for accepting our invitation to be here with us. It's very important. It's an honor for us to have you here today. Just let me introduce Professor David. I have a short bio here to read. So, David Fucci, sorry for the pronunciation, I'm not sure it's correct. Yeah, is an assistant professor in the software engineering department at the Blekinge Institute of Technology, where he works in the area of software quality, security, and requirements engineering. He's regularly part of Artifact Evaluation Committee at the International Conference of Software Engineering and the Requirements Engineering Conferences. And in 2018, he received the Open Data Recognition Award at the ISEM, the International Symposium on Empirical Software Engineering and Measurement. Congratulations on that. It's an honor for us to have you here again, David. So please be comfortable. As I said, you have about 1 hour and 15 to talk or interact with the audience for question and answers. We are in your command. Okay, the mic is yours. Thank you so much.
Thank you so much, Hudson. I think I should start by sharing my screen. And hopefully you can see the title slide.
Yes.
So hello, everybody.
That's okay.
Thank you.
It's okay.
Thank you so much again for having me. My name is Davide Fucci, and today I would like to talk a little bit about fair data and fair research. So basically looking at the current status in software engineering, the small step we can do to take on verification of our data, of our software. And to be a bit provocative, let's say the title of this talk is Software Engineering Research, and we're just snacking at the fair data buffet. So let's start. So first, something about my background to convince you that maybe I'm the right person to talk about this. Like Edson mentioned, I am currently a professor here at BTH. This is a picture of our beautiful campus, which looks particularly beautiful in summer, not so good in winter, I would say, or at least not as warm. And I'm also, importantly, at BTH, I'm part of the DAO group. This is the Data Access Unit group of the university, which has the goal of helping researchers sharing their scientific publication, their research data set. And I'm also part of the reference group of the Swedish National Data Service. So this is basically an organization that coordinates around the country with the different Swedish universities to bring open science practices for Swedish universities. And finally, maybe most importantly, in the research community of software engineering, I've been taking part in several artifact evaluation, as Edson mentioned, but also I have some experience, of course, firsthand in sharing my own research data, and that's why I was awarded this prize together with my colleagues, of course, in 2018 by the SM OpenScience Committee. So with that out of the way, let's have a look at the three main topics really that I would like to discuss today. So first of all, I'd like to establish a little bit of ground by defining what the FAIR principle of research data are. And since maybe some of you may not be familiar with them, I will go quite a lot in details in the definition of FAIR, and highlighting especially the differences with OpenScience as we go. Then I will give some insights on how FAIR happens, or it's happening to some extent in software engineering research and the neighboring field in computer science. And finally, I will also show a few examples on how to start with basic steps towards fair research from my own experience. And if you want to follow along with this presentation, or if you want to get your hands on this slide deck, I put a link here, so you can access that later on. Good. So OpenScience, I'm pretty sure if you're here, you're familiar with the term. In our community, actually, when we talk about OpenScience, mostly we mean those three things on top of this on top of this graph. So open source software, open data, and open access publication. This is not the whole story, at least according to the UN, who established this OpenScience as a set of those practices. And at least at the moment, our understanding, let's say, of OpenScience in software engineering is somehow limited to those three areas. However, there's more. There are more practices that still fall under this umbrella term of OpenScience. The one I'm showing here are related with focus on open engagement with social actors. And this is to some extent something that we try to do in our community through specialized tracks at conferences, such as Software Engineering in Societies tracks, or the RE community has something called RE Cares, which try to engage with the social and local actors. Then we have openness to diversity of scholarly knowledge and tradition, which is something that maybe doesn't really apply yet to software engineering. And then at the bottom of the slide, you can see there are other elements such as open educational resources, which is something our community is starting to work on, I would say. We have things such as open hardware and open infrastructure and open evaluation, which are getting, in a way, more and more popular. For example, a few conferences now have some registered reports tracks, which fall under the open evaluation practice. But then again, what is mainstream, I guess it's fair to assume at the moment, is that in software engineering, OpenScience is open source software, open data, open access publication. And in this context, actually, we have quite a number of initiatives. One of them is the ACM 6 of artifact evaluation. And this is an initiative that started in 2011 at FSE, the Foundation of Software Engineering Conference. And through the years, in the last 10, 11 years, became like commonplace in many other software engineering conferences. So the effort here, or the effort of this initiative, is to ensure that the tools and the data set from the articles that we publish in software engineering conferences are available, reusable, and somehow integrated in the publication process of the manuscript. So we augment the manuscript with the artifacts. And there's a working group at ACM, which is documenting and guiding the community in artifact evaluation, and they are doing a great effort in increasing both the authors but also the reviewers' participation. Although, as we will see later, they are having some troubles. And this group is currently led in software engineering by Jonathan Bell from Northwestern University in the United States. Then we have another initiative, which is the ACM Open Science Policies. And here the goal is to create, let's say, a blueprint for open science policies that should work for software engineering journals and conferences. And basically, these policies are the reason why many conferences nowadays, some journals, they have open science chairs, or why open science is explicitly mentioned in the call for paper of the conferences. And so if you're organizing a conference and you want to follow open science, definitely have a look at the document that you can find at this repository. This initiative is also led by another researcher, Daniel Grazietin, from the University of Stuttgart in Germany, which I actually would like to acknowledge as he gave me some good input when preparing this talk. Other initiatives that we have, and which I would like to mention, is the ACM artifact review and badging. Maybe many of you are familiar with those. So basically, papers published in conference and journals that follow this initiative can apply for one of these colorful badges here. And the point of the badges is to signal some properties of the artifacts that comes together with the paper. So without going into details, the two red badges, they indicate the artifact has been evaluated at different levels. The green badge indicates that the artifact has been it's been made available. And finally, we have the purple and blue badges that show that the study has been reproduced in total or in some parts of it with information extracted from the replication package. And last but not least, I would say, the other initiative that I'd like to bring up to show the commitment of, let's say, the community through some of the open science practices is the ACM transformative model for open access publication. So since at least 2013, I think ACM has been experimenting with different ways of open access, starting with green and gold open access. And now they recently released a new open access publishing model, which should transition ACM publication to be fully compliant with the Plan S. In case you're not familiar, Plan S is this initiative for open access publishing, which is lobbied basically, or is launched by an international consortium of research agencies. And they stated basically that the research funded by public grants must be immediately published in compliance with open access. So this is, ACM is reacting to this Plan S by establishing this transformative model for open access publication. So given this overview of initiatives, I hope that I convinced you that we are not doing that bad when it comes to open science and software engineering, at least according to those three red boxes that you see on top on the previous slide. So we have open publication, open data, open artifacts. But let's then look at other set of principles that you may have heard in the context of open research. And those are, of course, the topic of this presentation, the so-called FAIR principle, which stands for findable, accessible, interoperable, and reusable. So these guidelines, basically, they came about not long ago in 2016 by a group of researchers led by Wilkinson at the University of Madrid, a group of researchers mostly in the fields of biotechnology, bioinformatics, life sciences, and few of them in computer science. So there's a lot of authors on this paper. If you check it out, there's more than 30 authors, if I'm not wrong. A minor group of them is from computer sciences. Most of them are in biotechnology or life sciences. And we will see how much FAIR principle and life sciences are connected, so to speak. Anyways, they identified those 4 descriptive guidelines that they use to show how they envision research data management in the near future. So the first principle, F, stands for findable, which states that data objects should be uniquely and persistently identified. And here we see already the first difference between open science and FAIR. In FAIR, we don't really talk about data, we talk about data object. So what's a data object? It's basically anything that contains a data element, so the actual data that we want to publish, and very important, it's metadata. So data and metadata are packaged together in a data object, and this data object should be uniquely and persistently identifiable. So it's basically going to be archived, and it's going to be given some sort of unique ID that we can use to retrieve both data and metadata. The next one, the next principle is accessible. So those data objects should always be obtained by humans, and also importantly here, machines. And this is some of the things that I would like to stress about the FAIR principles, that they are not only for humans, they are also for, and most and foremost, for machines. And that happens, and that can happen, actually, the accessibility can happen upon appropriate authorization, which is another distinguishing factor compared to open data. So as opposed to open science, in which everything is usually supposed to be open and accessible, whereas in FAIR, we can have some form of authentication, as long as this authentication is, of course, readable by human, but also interpretable by machines. The third attribute is interoperability. So data objects, they need to be integrated with other data objects and interoperable within the research workflow. And there, it's where things start to get a bit more complicated. The idea on the long term is that eventually machines should be able to pull data objects from different sources and help researcher to integrate them in their studies or integrate them in the researcher workflow, or augment data sets that the researcher has created already. And finally, we have reusability. Reusable data object need to be well described in order to be replicated in different settings. This is not that far from the same guiding principle of OpenScience. So fostering replications of study in different contexts by different research groups or researcher in different settings. So we have some commonalities, but also some differences between FAIR and OpenScience, of course. And to summarize those, FAIR principle puts specific emphasis on the ability of machines to automatically find and use data in addition to support reuse by human. So first, focus on machine. Second, FAIR data is not necessarily open data. FAIR data can still be considered fair if behind authorization, licensing, or even payment. And we will see how this happens later on. So in OpenScience, like I said, we talk about generic research data. In FAIR, we talk about data object. So let's see how we can go from data to a digital data object that follows the FAIR principle. What are the different stages of this? So of course, we start with a totally unfair case. Neither the data or the metadata follows any of the research of the FAIR principle. We don't have an identifier for this data object. We don't archive this data object. So the next sensible thing to do is to make the data findable with a unique identifier so that it can be found by the other humans and possibly by machine. But at the moment, this is only usable by humans. The next level is to make the metadata fair. So to make them findable and available, but also interoperable and reusable. And once we have that, the next step is, of course, to have fair metadata, but the data itself has some restricted access. And like I mentioned before, this is completely okay as long as the authorization and the licensing part of the metadata is included as part of the data object. So basically, the metadata contains information about how you can use the data and who is supposed to use the data, to what extent. The next step is, of course, to have fair and open access data. So also our data, not only the metadata, is made openly available. So in this case, the data is completely open access. There's no authorization, anything like that. And finally, the next level goal, I would say, is that we have a fair environment where we have complete interoperability, which means that the data object is part of some sort of ecosystem, if you will, where we have mechanism to create, maintain, and reuse those data objects. We have ways for resolving the location of the data object in the environment. We have mechanism to retrieve the data objects through metadata, and mechanism to include this in the researcher workflow. One example of how to realize this environment is provided by the FAIR Digital Object Framework. So if you're interested, please, by any means, have a look at this. It's basically a specification for a framework for creating interoperability between data objects using semantic web technologies like RDF, for example. So we talk about data, but in the European Union, there's a big push, at least, to find ways of turning FAIR principles into reality. There's been and there are some projects sponsored by the European Union going on and on. And the output of, or part of the output for this effort is the establishment by the European Commission of a group of experts on FAIR research. And in one of the documents of these experts, you can find this statement where they basically realize that FAIR digital objects don't include only data, but also software or any other resources really used in research. And here the stress is on software intended as the software written to generate, process, analyze research results. And of course, in the case of software engineering, most of the time the software is actually what we want to publish, what we intend to publish. So I'm gonna, so this group actually also mapped the FAIR guidelines onto FAIR guidelines, so the FAIR guidelines for data onto FAIR guidelines for research software. And to better explain those 4 principles, they actually subdivided them into 15, let's say, sub-principles, if you will. So I'm going to show you a comparison between how they apply, this principle apply to data versus how they apply to software. So the first sub-principle it's for findability, is that data metadata are assigned a unique and persistent identifier. So this in terms of software means that the software and its metadata must have a unique identifier for each version, for each release of that software. The second sub-principle says that data are described with rich metadata, and we know that, I mentioned that before, and that doesn't change for software. The third sub-principle for findability says that metadata clearly and explicitly include identifier of the data it describes. So basically, there's a link between data and metadata, and this applies to software as well. Specifically for software, metadata should be clearly and explicitly include identifier for the different version of the software it describes. So basically mirroring what they say in the first principle for findability. Finally, data metadata should be registered in a searchable resource, which for software, this means we should have some sort of searchable software registry where we can find fair software. So this is about findability. Regarding accessibility instead, the first principle they identified says that metadata and data are retrievable by their identifier using a standard communication protocol. And this is the same for software. Now, in practice, the frameworks that actually implement FAIR principle are built on top of HTTP as a communication protocol. And this is convenient also because the second accessibility sub-principle says that the protocol should be open, free, and universally implementable. So this applies, of course, to data and software, and it's kind of a nice spot for using a protocol that we use already, such as HTTP. The next principle the next principle says that here fair data should allow for authorization. So although metadata should always be available. So if that's the case, this communication protocol should implement some sort of mechanism for authentications and authorization to access the data, and the same applies for research software. And finally, accessibility to metadata should be granted even when the data itself is no longer available. And this also applies for software, and this may be another difference compared to OpenScience, in which archival of data is forever. So we always have access to data in OpenScience, whereas in FAIR, archival access to metadata is forever. Another quite difference over there between OpenScience and FAIR software or FAIR research. Then looking at interoperability, the first principle says that metadata should use a formal, accessible, shared, and broadly applicable language for knowledge representation. So this is the same in terms of software. And what's happening here in practice is that this formal language is de facto becoming RDF, or Resource Description Framework, which is basically a way of describing a markup language for describing ontologies. And its representation, it's actually taking place in different formats. One of the most widespread and used is JSON-LD. Data metadata, says the next principle, should use vocabularies that follow FAIR principle. So this is also a very important point, because in software, we should create such shared vocabulary, but the software itself should take as input and produce output. So input data and output data that is also FAIR. So it's described using controlled vocabulary itself. Also very important things to take into account. And the last interoperability sub-principle says that data and metadata should include references to other data or metadata, so that we can basically create this network of data object. For software, this basically means creating a network of dependencies that can be referenced among each other. So all the libraries that our research software use should also be uniquely referenceable and accessible. And finally, for the last point, reusability. So the first principle here says that metadata and data should be richly described with a plurality of accurate and relevant attributes. And this applies for software as well. The second sub-principle says that metadata should be released with a clear and accessible usage license. Again, pointing to the fact that FAIR data is not necessarily open, And in the case of software, license should make clear the compatibility of the software dependencies. So the dependencies should have licenses that are not conflicting among themselves. And finally, or next, both research data and software need to have provenance, so some sort of clear origin of the data or the software and its version in the case of the software, like its authors, etc. And finally, for both software and research data, we should meet domain relevant and community standard. This is the last principle for reusability. And this is very important because if data objects are similar or similarly documented, it is easier to reuse them. And for software, it means that the documentation should also meet the standard. So this is another interesting point about FAIR. It's not something that must be applied to an entire research field, but it should be tailored for a subfield or for a sub-community that decides what to include in those standards. Like I show the example for data, how to get them in a fair state, so to speak. Let's see how we can make research software fair. So if we start again from a first totally unfair scenario in which we have source code and maybe we have some metadata, including the licenses, then we have the executable and its dependencies, but this is not archived, this doesn't have a unique identifier. So the first thing we do is to make this identifiable. So basically, we give the software some sort of DOI, which is something that we actually do in our community already. If you think about the integration between GitHub and Zenodo, where you can get the DOI from Zenodo for your software on GitHub or for your repository on GitHub. But then we work on the metadata. So we make the metadata of the software fair so that they are findable, accessible, and ideally interoperable and reusable by others. And the next stage is to have fair metadata with a license. In this case, the license can be restricting access to the executable, for example. So you release an executable, but this to be used executable needs some sort of authorization, which is captured in the license, which is also released together with the metadata. The next step, of course, will be to have a fair software, which has full access to the executable according to an open license. And an alternative would be to have a fair software where we have full access to the code, but only on the developer platform, such as GitHub. So the code, in this case, it's not fair because in the example of GitHub, there's no real archival of the code. The next step is also to archive the code, of course, and then we have fair software with archived fair code. And finally, we can have fair software, which is archived, completely reproducible, since we follow the FAIR principle for both the executable, the source code, and the dependencies of the executable. So this is the final stage, so to speak. Now, so we talk about fair data, we talk about fair software, and like I mentioned, biology, biochemistry, life sciences are the fields that are pushing a lot when it comes to fair principles. And in biology, biochemistry, etc., workflows are also considered part of the data itself. So perhaps we're not there yet in software engineering. So anyway, what is a workflow? It's defined as a precise description of the procedure that are used in research to coordinate different tasks and the dependency of those tasks on data. So basically the step that we follow in our research to go from some input to some intermediate results to generate some output, that it's what we usually publish in a paper. And since we usually do these workflows in code, at least nowadays, we have so-called computational workflows. And here in a computational workflow, basically each task represents the execution of a process, a call to an API, a call to a command line tool, or even executing of other workflows. So you see the example here, which I actually took from cancer research. This workflow can be transformed into a fair data object in order for other people or machines to reuse the entirety of it or parts of it. Oops. So if you look at the workflow, first of all, it's findable since it has a permanent URL. It has a unique ID. It is available on a search engine that allows to search for workflows based on metadata. In this case, this example is taken from, of course, a European project called workflowapp.eu. And then you see its components here in those colorful boxes. So we have inputs in the blue boxes on top. Then we have data flows, so the arrows are indicating how data flows from one box to the other. The yellow boxes are tools, so basically these command line tools or API calls, whatever. And we have nested workflows in the orange boxes. So finally here at the bottom in the other blue box, you can see the output. And there's also a license or a reference to a license to make this workflow accessible by other workflows, or of course by humans. There's a lot of metadata associated to it, so providing basically a specification for the input, the output, and the steps. So as you can see, we have a name for each of the input. For example, on top, input can be a reference to another file. It can be an integer, it can be a Boolean. We have each step in the workflows. There's a reference with a permanent link with where these steps are actually described in a formal language. So another basically language to define ontologies specifically for the workflow. In this case, the language is called CWL, which is basically an adaptation of RDF to describe workflows. And so here you can describe each step. So for example, zipping a file or combining files together, you can indicate whether this workflow is produced by a tool rather than a sub workflow. And finally, at the bottom, we have a description of the output and some metadata retrievable in different machine parsable formats. So workflows, you can call them pipeline, you can call them research procedures. They are also data objects, and therefore they can be made fair. And this is something, like I mentioned, that where we are maybe not truly considering in software engineering research at the moment, I would say. There is also an attempt here at making a map between fair data principles and workflow. And the situation here is not as clear as for fair software. So in fact, when it comes to the first findability principle on top here, you can see that metadata, of course, need to have assigned a global, unique, and persistent ID. But we see that naming convention on how to create those IDs are still being devised by the workflow community. For the second findability principle, data, described with rich metadata, here we have some workflow repositories, like the one I showed you before, workflowapp.eu. And for the fourth findability principle, data metadata are registered or indexed in searchable resources. We also have, of course, ways of searching through metadata on this search engines for workflows. Another accessibility, and for accessibility actually, regarding authentication and authorization, many of those workflow systems have steps that indicate whether the task executed in the workflow necessitates some sort of authorization. So there's metadata attached to each of the steps that tells you if you're authorized to take that step and how you can get authorization to get that step. And finally, when it comes to interoperability, there are already some good results in the workflow community. The data used by the workflow itself, and the metadata can be already referenced by each other, which is particularly useful when, for example, creating some sub workflows, which can be reused in other workflows. And if you're interested in this idea of workflows and fair workflows, and you want to apply to your research, I guess that in software engineering, we're quite fond of Jupyter Notebook, and there's some nice extensions for Jupyter and the Python library that accompanies this Jupyter extension, which is called Fair Workflow, which basically allow you to annotate each functions that composes your workflow to create a fair model of the workflow. I'm going to show you an example here. If you think of a workflow basically as a series of functions that modify data until they produce an output, you can annotate those functions. So the step in the workflows in this special annotation will translate to a RDF representation of it. So to this ontological representation of that step. Similarly, there's an annotation provided by this framework to create an entire workflow given the steps, and of course translated to RDF format, so to ontological format, which can be interpreted by machines as well. And finally, possibly most importantly, you can also publish the workflow. You can add metadata to your workflow, such as authorship, and you can publish it as a nano publication. So a nano publication, actually, it's something that comes, again, from the field of biotechnology and life sciences. In nanotechnology, in biotechnology, a nano publication, actually, it's a very small unit of publishable information, basically. So one example from life sciences of a nano publication would be a nano publication reporting the relationship between a single gene and a disease. So one fact, that's the entire publication, a single fact. So nano publications are expressed usually in publication, machine readable ways. So the idea is to disseminate individual unit of knowledge independently from the larger publication. And those are usually made of three parts. Assertion, so this is the main content of the nano publication. The provenance is the part that describes how this assertion came to be, basically. This can include, for example, references to the scientific method that was used to generate the assertion, or references to the study which was actually performed that came up with that assertion. Finally, we have also publication information. This is basically metadata, such as the author, the date of creation, the license, and so on. So this is a nice tool that you can already use to experiment a little bit with making the workflows that we have in software engineer, especially if it's based on Jupyter Notebook, experimenting with creating this fair workflow. So now we have an overview of FAIR in terms of data, software, but also workflows. Let's have a look at how are we doing in software engineering. So if I summarize the answer to this question in one word, I came up with this. So we're mostly F'd in the sense that we're mostly working on findability and overlooking accessibility, interoperability, and reproducibility. So the focus is on findability. And there are some good news, especially regarding findability, as I mentioned. This is some result I'm showing from a survey of the ACM digital library by Asselbring and colleagues, published a few years back. And they show that out of all the papers in the HCM digital libraries that mention a GitHub repository, 27% are published in the area of software engineering. So among all the computer science, software engineering accounts for 27% of the GitHub repositories mentioned in scientific papers, basically. And this is good. It means that as a field, we're actually at least sharing these repositories. Somehow we make them findable. The bad news is, and this result actually here applies to the entire computer science field, but I fear that it will hold true also for software engineering. The drawbacks I was saying is that repositories have a median life of 15 days. So basically it means that someone puts up their research artifact, their data, makes it findable on GitHub before the artifact evaluation deadline, does some modification because the reviewer asked them to do some modification, then they forget about it and they move on to the next study. Even worse, what they show is that 1/3 of those repositories actually have activities for 1 day or less. So yeah, that doesn't sound reassuring at the moment. And the good thing, or perhaps the bad thing, is that we are not alone. In a closely related field like human-computer interaction, things are not that brighter. Here I'm reporting some results from a study from 2012, which surveyed the 2020, sorry, which surveyed the previous two editions of CHI, so the edition 2018 and 2019 of the International Conference on Human-Computer Interaction. And they show that only between 27 and 37% of the artifacts that are reported in publication at CHI, which is, by the way, a huge conference, are actually shared. More than 40%, it's actually processed data, so we don't know how this data came to be. We just have the final product in most of the cases, in 40% of the cases. But then when we look at the raw data or data processing procedure or workflow, if you want, only 25% of those are shared. And the same holds for prototypes, where we have a sharing percentage of a bit over 25%. And when asked about the reason against sharing, the author mostly said that it's because they want to avoid publishing sensitive data or data they don't have permission to publish, which again points to the fact that it's maybe time to start thinking about separating data from metadata, in the sense that even sensitive or licensed data can be published, or the metadata of this data can be published if we follow the FAIR principle. Finally, it's also interesting to see that the last two reasons they gave is that there's no sensible use for the data. So basically pointing out to the fact that it's difficult to make use, integrate this data with other or similar data set. So possibly here we have some room to investigate interoperability among different data objects, and this can maybe will give people a chance or an incentive to publish their data, but also to acquire data published by others and to integrate data published by different researchers. In software engineering, we also have some data regarding the sharing of research artifact, and this is a study published in Empirical Software Engineering last year by Temperley and other colleagues at Carnegie Mellon University. And they show that 2/3 of papers published in big conferences and journals in software engineering between 2014 and 2018 contain an artifact, which is good. What is also good is that the proportion of papers containing those artifacts are growing almost by 20% between 2014 and 2018. Interestingly, in the study, they also interview authors who actually share the artifact. And one quote they reported in the paper actually struck me. They say, some artifacts are dangerous, difficult, or impossible to share due to privacy or intellectual property concern, which again points to this understanding of data as only data without metadata. So if there is something we can do better, definitely it's to decouple data from metadata, applying proper licensing when sharing both of them. There's something definitely that we can learn, that our community can learn from the FAIR principle number 2. And this is basically the idea that data is always described with rich metadata. Of course, the next step is to understand what this rich metadata is. And this is something that each subcommunity in software engineering should take care of, I believe. Another interesting study is from Ehrman and colleagues. This is published at the FSE Foundation of Software Engineering Conference 2020. They look at how committees, artifact evaluation committees, perceive the actual artifact evaluation. So they survey 147 members of artifact evaluation committees across, let's say, big conferences in software engineering, programming language, and databases, and look at what's their perception versus the content of the call for artifact. So there's some interesting results there. So first of all, and foremost, I would say, about the definition of data quality. So there's no consensus on what data quality on an artifact should be. In general, in this study, they observed that this definition of qualities varies a lot according to artifact type across different conferences and over time, of course. So here, as a community, we can focus a little bit more on what the guidelines about reusability say. So data metadata should meet domain relevant community standard. Again, it's easier to evaluate a data set if they are similar among each other. So same type of data organized in a standardized way needs to be well established, well documented, but it has to come from our subcommunities. And the different subcommunities in software engineering should have some minimal information standard which can help us to express what the quality of the artifact is, and as a direct effect, actually improve the reusability of that artifact. The other quote that struck with me is this one. We also find problematic inconsistency in terminology used to express artifact evaluation. And this, again, is something that can be addressed by following some of the FAIR principles. So for example, the interoperability principle number 2, that data metadata should use shared vocabularies, which basically can be control vocabulary used to describe dataset and which are attached as the documentation to that dataset, which are findable and that are accessible to anyone who produces the data, either for use or for review, for example. In the same study, Herman and colleagues, they look at what is the purpose of the artifact evaluation according to the call for artifact itself. So they reviewed 71 calls of the same conference that I mentioned before between 2011 and 2019, and they look at the purpose versus the author's expectations. And so across all the call that they analyzed, they show that the most frequent purpose stated in the artifact, in the call for artifact, was to reuse artifact, followed by reproducibility, followed by comparison. Although 1 out of 5 of those calls actually doesn't really state the purpose, which is already a bit scary. And then from the author's perspective, this creates confusion on how to best prepare the artifact and what to expect once the artifact evaluated if the purpose of the call is not clearly stated. So here again, probably using FAIR principle as guidelines in the artifact call may improve the situation and clarify a little bit this confusion. Finally, they also look at what the reviewers perceive to be the purpose of the artifact call, and they found yet another mismatch here. So although the purpose of the artifact evaluation in principle is to validate the results presented in the paper from the reviewer's perspective, they were most interested in fostering replicability, reusability, which of course it's not bad, it just causes confusion. So accordingly, the reviewer focused on quality criteria that address this concern, replicability and reusability, rather than validation. And moreover, they expect different quality criteria for different artifacts, but those are not communicated in the call for artifacts itself. And to add insult to injury, I would say, it seems that less than half of the reviewers have actually experience with artifact reviews. So there's a mismatch between the goals of the call for paper or call for artifact, the artifact evaluation, the goals of the reviewers, and the skills of the reviewers. And again, here, I believe that FAIR principle can be put in good use to align the qualities fostered in artifact evaluation calls, align them with the reviewers, align them with the expectation from the authors. So one problem, of course, still stands is that the reviewers themselves, they have to have experience with data verification and how to apply those principles. I've also done a survey myself when preparing for this talk last summer, and I involved artifact evaluation committees. I think I wrote to about 200 people involved in big software engineering conference, artifact evaluation committee over the last 5 years. 24 of them were kind enough to take some time to answer this survey. And I asked them about the perception they have of the FAIR principle. So this is what I found. Most perceive that software engineering research data, and there I focused explicitly on data rather than softwares, on research artifacts, because we need to start from somewhere. So they stated that research data has to be findable. There's some support for accessibility, but as you can see, interoperability and reusability are not perceived to be that important. Just to reiterate, we're focusing on findability at the moment. I've also collected a bit more of qualitative answers about how to make research data in software engineering more fair. And here I'm showing the analysis of free-form answers starting from findability. Here you can see from the free text that the word DOI is dominating, which makes sense. This is also what many of us are doing nowadays. We share research data on platforms that provide us a unique identifier for that data on top of the paper. One answer was particularly interesting to me. They say one possible route can be to publish artifacts permanently, hosted and available, and use a common standard to make artifacts searchable. And this is a very important idea here. We are reaching now a point in which, yes, we have artifacts that are shared, maybe using 2 or 3 platforms, but soon they will become hard to find, or maybe they're already hard to find. So perhaps the next step will be working on a solution to make them easier to find, which, in my opinion, implies working on associating better metadata to our data, to our replication package, to make them easier to find. Then I asked them about accessibility. There's no concept here really that seems to have a prevalence. One that particularly interests me is the retrieval of research data. And somebody proposed to use FAIR templates for different type of data set in order for them to be retrievable and accessible later. And this is actually another interesting idea, which myself and some colleagues have implemented in our own work, which I hope to show you soon. The next one is interoperability. And here we can see the keyword that's standing a little bit, it's different. So this is pointing to the fact that different sources need to be integrated. And in the answer, our respondent pointed out that there's a need for a standardized syntax for describing data. And interestingly, they say that at the moment, we are in the process of understanding how to organize information for repositories, but we are far away for a common agreement. And this is also very true, in my opinion. I think this is an effort that should take place within each community in software engineering. We should start looking at what is good metadata that we can use to describe our own data and create data objects. Not necessarily fair data object, but at least create data objects that contain good data, but also good metadata. And the final question was about reusability, of course. Also here, there's kind of a mixed bag of answers. I just picked two interesting keywords here, information and standard, pointing to the fact that we need some sort of predefined set of information or predefined standard for documenting research data. And here respondent said, provide a predefined form which include rich and accurate information. This way we could actually force, in a way, a researcher to collect metadata, made mandatory the usage of such form during, for example, the publication process that can help getting a clear pictures about metadata, including licenses, provenance, and so on. So for the last part of this talk, I'm going to conclude by showing you a couple of examples from my own research that are very first initial step towards supporting data objects and their verification in the field, specifically of requirements engineering research. So the first thing I'd like to talk about is requirements quality factors. So we know that text-based requirements have some quality factors associated to them. This is the same way that source code does. So for example, readability is one of such quality factors. And we created an ontology based on the literature to have an idea to organize those quality factors. So here the idea of creating this ontology is to follow a little bit the interoperability principle, especially the one regarding the use of controlled vocabularies. So the fact that metadata and data should have a formal, accessible, shared, broadly applicable language for knowledge representation. And in this case, the knowledge is a knowledge representation of a very specific field, so requirements quality factors. And to act upon this, actually, there is one great resource that I recommend everybody to check, is the GoFair website. So this website, basically for each principle, and the principle, as you notice, they are very descriptive. The GoFair website offers a bit more prescriptive, actionable advices on how to act upon each of the principles. So for this principle, they suggest that if data object has not been yet described in a public vocabulary or on an ontology, then you should try to create a vocabulary of your own, which is what we did actually. And we publish this ontology, make it public, open, and use a machine readable format to present it. And so what we got here as this initial ontology of different quality factors organized around the attributes that we extracted from the literature. Now, here you're looking at a nice user interface where you can basically filter and categorize and look at the provenance of each of those quality factors. But also we made it available in a machine readable format using JSON, JSON-LD. The other example is from another subfield of requirements engineering, which is NLP for RE, or the application of natural language processing techniques to requirements engineering problems. And here we tackle explicitly the issue of describing a data set using metadata, which is basically what the F2 principle, findability 2 principle recommends. And again, we went and looked at the GoFair recommendation, and they say that metadata should include the descriptive information of the context, the quality, the condition, and the characteristics of the data. Importantly, in the GoFair, they stress how rich metadata allows a computer to automatically accomplish those tasks that currently demand attention and time from the researcher. So what we have been doing basically is collecting studies from the field of natural language processing for requirements engineering, look at the attribute of dataset algorithms, evaluations, criteria, annotators of the dataset, and so on, and created a template, which we then expanded or condensed based on interviews with experts. So this is what we have. This is kind of working quite well. It's currently under review. And the important thing is this applies to a very narrow field. So at the very narrow field of NLP for RE study, which it's in the requirements engineering, something that it's still new, I would say. So, and it's just the first step towards creating rich metadata description of the data that are eventually found in this kind of studies. So we hope that this metadata collection can make these studies later on easier to find. You can, sort and filter those studies by different attributes according to this list of metadata, and easier to find, to filter, using more richer way of looking at this data or sorting this data. Right. I think I'm soon running out of time, so I would like to conclude my talks with few takeaways. So what you should take home from this. First and foremost, that FAIR principles and OpenScience are different, although they have some commonalities. On the long term, FAIR principle focus on involving machine in the research process. And they stress the importance of data objects. So data plus metadata in machine readable and interpretable formats. Currently, we are focusing as a software engineering research field on findability of research data, at least, neglecting a bit accessibility, reusability, and interoperability. And finally, like I showed in the last two examples, we can start very small by creating ontologies for small subfields that are machine readable. We don't have to aim for fully interoperable data from the start, or from fully interoperable software and software dependencies from the start, or from fully interoperable workflows from the start. It's too early. We can focus on data sets rather than on software. We can focus on specific aspects of the FAIR rather than on all of them at the same time, and then work up from there. That really concludes my talk. You can access the slides and the reading list, which I used, and I based most of my talk on this reading list. I also collected survey data, which I'm happy to share with you. And last but not least, in the last link, you can fill in a survey. You can do it right now, which is supported by a nonprofit organization founded by the European Union called FairAware. The aim here of this association is to understand the perception that researchers have of the FAIR artifacts and of FAIR principles. So if you visit this URL or you use the QR code, you will find in the survey a field called course identification. So please type OpenScience 22 uppercase when you fill in the data, so I can collect, and we can maybe later on even share with you what is the perception of the community regarding FAIR artifacts, FAIR principle in software engineering. That's pretty much it. Thank you so much for listening to this talk, and I'm open for questions.
Thank you, Professor Davide Fucci. We have time for some questions. Anyone?
I wasn't keeping an eye on the chat, but
no one have written any question, you can just open your mic and state with Professor Davide.
I guess everybody's busy taking the survey.
Okay, so I will start doing one as I wrote here. First of all, thank you again, Professor. It was a great and nice and enlightening talk. Yeah. In your talk, you showed that we have a lot of challenges to reach the ideal state of openness in our research, especially software engineering. In your opinion, what should be a research agenda for us to tackle in this field of open science and fair in software engineering?
The very basic step is to work on metadata. That I cannot stress this more, because if you don't have metadata, everything else falls apart. Like every time you create a data set, it's, I don't know, a CS, Excel sheet, or whatever format, you have to provide metadata that describes the data in, not in text, hopefully, but in a computational form. So some format like JSON-LD, it's very lightweight. It's basically JSON with extra fields, so that in the long run, that the metadata can be interoperable, supported by a machine. So machine can go and grab your data set because it's described in a way that matches a query from maybe another machine that needs that data to augment an existing data set. So what you do now is that you have your data set, and maybe you go and look at similar data set and compare. Ideally, in the future, machines will do this. This is very long-term thinking, but without metadata that properly describes the data and enables machine to do that, we'll never get there.
So after the first question, I think that the others could think of one question more. So we have time now.
It's fine if people don't have questions. But fill in the survey, please.
Okay, so I'll try another one.
Sure.
You also showed that we as researchers can move toward data flow. You showed how we can move towards fair data and fair workflows. And also, as you also mentioned now in your first answer, that metadata is the really important part. Would it be this the first step towards moving this fair for both data and workflows, or is it different for tackling data and workflows in a different way?
Maybe it's I see that there's a lot of commonalities in the way, at least in the technologies that there exist to describe workflows. It's just that as a software engineering community, we are not used to it. We're definitely years behind life sciences in the use of computational workflows. We do Jupyter notebooks, but we don't really think of them in terms of workflows. So in my opinion, to answer your question, is that the technologies are there. Maybe the focus should not be on the things where we are not that good at yet. So we're quite good. We're doing quite good at sharing data. So let's focus on that. Let's make it better, rather than jumping on something where we are, let's say, a bit behind or we're not used to yet. Like thinking in terms of computational workflows, like life science researchers do.
Okay, thank you. Anyone? Any more questions? Okay, then I will continue. We have still time. You still have time, so you can continue thinking another question. And so, what about tools to fulfill this path towards fair data? Is it we have plenty enough, like OpenScience framework, or we still need more tooling for such endeavor?
Yeah, from a tooling perspective, I mentioned JSON LD. I'm going to write it in the chat so everybody has access to it. This is not a tool, it's just like a grammar for JSON that allows you to have in a very lightweight format, a way of annotating data that is parsable. So I would say that's not a tool, but it's the basic thing we can do. Another important resource is to make, once you have this metadata available, to make it findable for other people. It's a website called schema.org. This is kind of a search engine for metadata in a way. So to tackle the very first initial point of making findable through metadata, those two tools, if you will, in my opinion, are the essential thing. And like I mentioned, for workflows, the state of the art is CWL, which is nothing else than just another way of annotating workflow step. And I can drop more names. One important one, if you want to look at annotations of workflows and making workflows fair, is arrow crate, research object crate. So like a crate of different research objects to make them interoperable. It's basically the next step in workflow, in fair workflow. So making workflow and part of the workflows reusable among each other. So I can take a part of the workflows that I need there, another sub workflow, and put them together in my own. And to describe this, I use a framework which is called Arrow Crate. They have a GitHub repositories. I'm pretty sure this is also something sponsored by European Union. Usually they are. There's a lot in Europe. There's a lot to push towards a lot of money in this kind of meta research around fair data.
Okay, thank you, Professor Davide. Once more. Anyone? Questions? Okay, Carlos Silva just read something in chat. I'm just a newcomer.
That's very nice.
Okay.
That's very nice, Carlo. Yeah. I hope it helps. At least you have some references to go and dig.
Okay.
Yeah.
So let's thank you, Professor Davide Fucci, for his presentation.
Thank you.
His explanation on the end.
Thank you so much.
Thank you very much for your talk.
Thank you, and I wish everybody wish you well for the next for the rest of the conference and the workshop. Thank you so much again for having me.
Thank you. Just to remind everyone that we have an interval right now, and then we are coming back to discuss maybe one research agenda as explained before by Professor Edson Oliveira in the beginning. And I hope to see you at 10:45 for this research agenda discussion that we're going to have in this room. Okay, thank you.
Take care, everybody. Thank you again for having me. Bye. Bye.
Bye.
Bye.